We're in a chapter on derivatives. I know that's pretty obvious, but if you think about it, we're learning how to do the derivative of many different kinds of functions. If you go back with me to the beginning of the chapter, we learned how to do the derivative of basic power functions, like x squared. And then we learned how to do quotients and products. Quickly, though, we realized that there's other functions out there, like a trig function. You do the derivative of sine. Okay, and then we started to combine functions together. We call that a chain rule or a composition, which requires the chain rule. Okay, what you just took a quiz on was implicit. Now, those aren't functions. Those are just equations for the sake of being an equation full of variables. But we're going to now go back to more functions. And one of those types of functions is an inverse trig function. Now, an inverse trig function is going to require a new rule. And just like the derivative of sine required a rule to be cosine, so will the derivative of inverse sine. Now, first off, you got to realize that inverse sine is like a whole different kind of function. Inverse sine is that graph. Now, if you didn't remember that graph before coming to class, don't worry about it. But the bottom line is I just want you to realize that's a different kind of graph. And so it's got a different kind of derivative. In other words, it's got a different slope. Now, we could talk about some slopes along this graph. We'll do that after we come up with a formula. So, how are we going to do the derivative of inverse sine? Okay, just to make sure that you're getting the idea. Since this is a new function, it needs a new rule. And so trying to apply an old rule, like, saying that the derivative of sine is cosine, so that means the derivative of inverse sine is inverse cosine. Trying to apply an old rule, okay, would be kind of silly, okay, because it turns out that the slope of that graph would have nothing to do with that equation. However, if we look at this inverse sine through a slightly different lens, if we look at this inverse sine through an implicit lens, now what I'm doing here is I'm changing the equation. I'm changing the equation to be implicitly solved for y. In other words, I brought the sine over to the other side. Well, now that is a regular sine equation. You say, but it's the sine of y. Yeah, but we know how to do the derivative of the sine of y. I'm going to draw a little line here because I want you to realize that above the line we did algebra. Below the line is going to be the calculus. So again, we can do the derivative of a regular sine. It's too easy, right? The derivative of sine is cosine. Now leave the inside alone. That's why we're writing down the letter y. And then do the derivative of the inside, which means dy dx. Okay, and then of course the derivative of x is 1. Now keep in mind what's happening here. We're doing the derivative of y equals the inverse sine of x, but we did it implicitly because we changed the equation to be sine of y equals x. Now I just did the derivative, and now we can solve for dy dx. You can divide both sides by cosine of y. Now, everything that's on the board is correct. The problem is it's not done yet. It's not done yet. I will have students say that you could change this to be the secant of y. And I'll say to you, it's better, but it's still not done yet. And so we'll pick up how to improve this answer when you guys come back from lunch. All right, so do you realize that we've just opened up another can? It's the inverse can. How do you do the derivative of an inverse? I'm trying to get you the idea that we need something new. Now, it turns out that we kind of did a little switcheroo so that we could use an implicit method. I guess that's not officially new, but there's something that's just not quite good enough about this answer. Notice I didn't say it's wrong. It's just not quite good enough. Let me explain. The original problem was a function. Functions are nice. They're in terms of x. Most things in math work that way. That means the derivative should be equally nice. That means the derivative should be in terms of x. Now, it would be silly to say, oh, so just cosine of x. No, that's a whole different idea. It was the cosine of y because of the way we changed the problem. And to be clear, there's nothing wrong with what we did up here. But what we are going to do is we're going to do a little magic and change cosine of y. Now, this whole thing about secant, that was a good call, but it's equally not good enough because it's got a y in it. I don't want a y in my answer if my original problem started out as a function of x. All right. Now, I wouldn't expect you guys just to pull this little trick out of the bag, but I do think that you can understand it 100%. So the little trick that we kind of pull out of the bag over here is from our Trig tricks, our Trig tricks. It turns out that actually today in class, I taught a group of students that cosine squared plus sine squared equals 1. But you already knew that. But look what I'm doing. I'm making the statement using y. Now, that's fine, because one of the things that you should have learned from trigonometry is that this identity is true for any variable. It doesn't matter if it's theta, doesn't matter if it's x, doesn't matter if it's y. Okay, so we're doing a little trick here, kind of off to the side. Now, just so you can kind of see where this is going, and it's not just like random math that I'm putting on the board. Remember this cosine of y down here? Want to change it. Okay, want to change it. Oh, I have a cosine of y up here. Okay, now it's not, you can't just change it to be 1 minus sine squared, because that's not really going to fix the problem. But if we go over here to the original problem, or check that, if I go over here to my implicit version, I can do another trick. And that is that I can equally claim that sine squared equals x squared. Sine squared equals x squared. Now, that's pretty snappy. That's pretty snazzy. It's snappy too, but because what happened here is I was able to change x and y. I was able to make a switch. And now, if you solve this for cosine, if I solve this for cosine, all of a sudden I'm able to make a statement that uses x. A statement that uses x. It's also a statement that uses a square root and a 1 minus x squared. Okay, so remember this cosine down here? By math, not magic, but by math, it's equal to the square root of 1 minus x squared. That means the derivative is equal to 1 over the square root of 1 minus x squared. Now that derivative is better. Interesting, just because it's in terms of x. Even though this derivative was correct, it was in terms of y. But now that it's in terms of x, we would say that it's better, again, because the original problem was a function of x. What do you think? Do you just sort of believe me? Let's kind of do a little bit of a geometric observation. Basically, a little observation about some slopes. Now, what I'm doing here is going back to this graph, and I'm picking out some x places. There's an x place that has a particular slope. Okay, I don't expect you to know, but if maybe you had to make a guess, or maybe that we're going to actually plug in 0. You can kind of see that it makes sense. Again, if I plug in 0 to my sort of new and improved formula, out pops 1. Out pops the number 1. I don't have a ruler, but you guys have been around math enough to know that sometimes there's special slopes. And basically, we're right in the middle right there. That actually would be a slope of 1. So my little formula seems legit. Here's a place that's a little easier to kind of affirm. At x equals 1, we seem to have a vertical line. Remember? Remember what happens when you have the slope of a vertical line from like your algebra class? Okay, well here we can see exactly what we suspect. I got to squeeze this in here, but I'm plugging in the number 1 into my new and improved formula. I'm getting 1 over the square root of 1 minus 1 squared, which we know would be the same as 1 over 0. Basically, a rise of 1, but a run of 0. And of course, when you have a run of 0, we would say that it's a vertical line or it's an undefined slope. All I'm trying to do is kind of prove to you guys that my formula, and it's not my formula, but our inverse formula here is legit. Okay, it actually gives you those slopes. Okay, now inverse derivatives or derivatives of inverses, they are of a, I'm going to skip that. They are, and I'm going to skip that too, but they're of kind of a different breed. And the breed is that they are formulas. They're formulas. And we will want to know 3 of them. Don't worry if you're like, oh my gosh, you're going to put down like 6 formulas for sine, cosine, tangent. No, we're actually going to just do 3 of them. Now here's the one that we just did. Notice though that it's given in a little different format. It's in terms of u. I encourage you to write it down in terms of u. So it says that the derivative of inverse sine of u is equal to 1 over the square root of 1 minus u squared times du dx. What's this u thing? You're going to see it almost in every rule that we do to the end of this chapter. You're going to see it in like every rule. So I want to make sure that you realize that it's just telling you that you would use the chain rule. Okay? Maybe you would say, yeah, of course I would use the chain rule. I mean, I think you would when I give you a problem, but it's basically telling you to leave the inside alone. So I leave the inside alone, leave it as a u, or whatever it is, and then you have to do the derivative of the inside. The derivative of the inside, du dx. Okay, now when it's actually a problem, there's actual numbers there, then you'll change them as appropriate. U, it just stands for the inside. The inside. Inverse tangent, it's a rule. It's a rule. Boo. Actually, no, it's not. Doesn't have to be bad. Inverse tangent, we didn't prove it, but it would have some similarities to what we just did. turns out to be 1 over 1 plus u squared. This is a big one. You guys will use this throughout the entire year. Trust me, we get to like March. Okay, you'll definitely be like, okay, yeah, inverse tangent is 1 over 1 plus u squared. That's the derivative. The reason I said March is because at that time we'll be doing these rules backwards. And so you'll really kind of be like, oh, yeah. This one, if I go backwards, goes back to inverse tangent. That's an integral, by the way. Okay, basically doing everything backwards. Here's one more. I only make you do 3. Inverse secant. This one's got a little bit more commotion. It's got this absolute value. That's an absolute value in the denominator. Inverse secant. 1 over the absolute value of u times the square root of u squared minus 1 times du dx. Now, I don't make you come up to my desk and rattle these off. We only do that one time, otherwise it gets old. But you do have to memorize these. Some of calculus is memorizing. All right, so when eventually it comes time for the test, you should have these 3 memorized. Let's make sure we understand that if I give you an inverse trig function, it's rule time. You're supposed to plug it into these rules. Who doesn't like a rule now and then? You just plug into it. So I don't want to say I don't have to do too much thinking, but don't do too much thinking. Trust the rule. The rule for inverse tangent is 1 over 1 plus. So it's literally going to always be 1 over 1 plus. And then this u squared. Now here's where we have to be aware that u squared is referring to the 4t cubed. The 4t cubed. Which we will simplify. I just want to show you that I'm plugging into the rule. Now, you always do the derivative of the inside. Right now, we did the derivative of the outside. The derivative of the outside was the rule. The derivative of the inside, well, that's, of course, the chain piece. So we're going to do the derivative of 4t cubed. We get 12t squared. I just mixed up the variable that you guys start to get comfortable with other variables. It's no different than x. And then we should simplify. Looks like we'll get 12t squared in the numerator. And then we'll get a 1 plus. I would expect to see you change this to 16. Make sure you change it to 16. And then remember, you multiply these exponents. Multiply 3 times 2. We get t to the 6. Okay, don't do too much more. Like, there's nothing else to do, but don't try to simplify here. The fraction's kind of like the wrong way. I can't do a Hart method. The denominator has 2 terms. So nothing simplifies. Here's my plan, by the way. We're going to do a couple more problems today. We'll do a few more at the beginning of the period tomorrow. I give you kind of like a partial work period tomorrow. Basically, we're not going to start the next section tomorrow, but since we'll start the next section Thursday, we'll give you a little time just to get working on this section. All right, but how about the inverse sine? Y equals the inverse sine of the square root of 5 times x. The inverse sine of the square root of 5 times x. For some reason, calculus books and math teachers like you to be comfortable when you see like square root signs. Here, the square root sign is only on the 5. So we don't need to overthink this. Listen, overthinking this would be trying to do something with a 1/2. Like maybe like something like 5x to the 1/2. That's actually not needed because it's not x to the 1/2. Okay, it's only the square root of 5. The x is actually to the first power. You guys did a nice job with the square root problem on the mini check. Nice job with that. Just don't overthink that. It's the square root of 5 as a coefficient. So let's plug it into the rule. 1 over the square root of 1 minus u squared. 1 over the square root of 1 minus u squared. Times the derivative of the inside. Now, when it comes time to do the derivative of the inside, it's just the square root of 5 times x to the first power. So it's just going to come out to be the coefficient. We're going to multiply the square root of 5 onto the end of this. As I said, you don't want to overthink that as some type of 1/2. It's not needed. Also, the reason we're obviously going over some of these is that you guys understand kind of how to simplify. And what I'm showing you here is fine. In other words, putting the square root up in the top. What else? 1 minus. It looks like we should square this. I would expect that you square it to be 5x squared. So 1 minus 5x squared. Now, we get in a little bit of gray area. I'll just be honest, I kind of almost hate to say this because I like to be consistent. Math is consistent. But what I'm about to say is not necessarily consistent. But it seems to be a little gray area where we sort of look the other way. There's a square root in the denominator. Okay, yes, there's a square root down there. It turns out that for some reason, when it comes to inverse trig functions, that it's okay to leave that square root in that answer. And yeah, I almost don't even like saying it, but you don't need to multiply the top and bottom by this. I mean, we could, but I'm giving you sort of permission that the answer is okay to be written as it was in white. If for some reason you have a teacher that doesn't allow that, okay, you could take one more step and you could, of course, simplify the bottom. You could get without the square root down there. Just so you know, the 5 is going to distribute in here. I'm allowed to put them together. But as I write this down, I'm even saying that you don't have to do this. As every answer I've ever seen stays this way. Okay? Not that this is wrong, and I don't know. It actually is more consistent. For some reason, because it's an inverse and it has that in the rule, we sort of look the other way. All right, well, we'll let that kind of be our own little secret there. Let's do one more problem, and then we'll call it a day. You guys, good sports, usually working pretty hard here. But this one's not bad to do today. You know what? I'm going to change. Let's save this one for tomorrow. It's got some extra simplifying. We don't need to squeeze it in here before the bell. All right, so I'll have a couple more examples tomorrow. Honestly, probably before lunch, but definitely after lunch. You would have some time to start this assignment, and I hope that you'll do that.